In previous lectures, we've seen some examples of Markov chains where we said states have different properties. Let's talk about classification of these states. Now, remember that Pij refers to the probability that the state at time n equals j when the state at time 0 was I. So this is the conditional probability of going from I to j in n steps. Now, let's make a definition. We define a state to be recurrent. So state I is recurrent, also known as persistent, if the probability that xn is equal to I for some n greater or equal to 1, given that the Markov chain started in state I, is 1. This means that given that the process started in state I, it will return to state I at some time in the future with probability 1. Otherwise, state I is known as transient. Otherwise, it is transient. Okay, so we can easily prove a theorem using the Borel-Cantelli lemmas based on this definition. State J is recurrent or persistent if the sum over n, Pjj of n, is infinite. And part B, state J is transient if the summation over all time Pjj of n is less than infinity. The proof is really easy. Notice what Pjj of n is. It is the probability, let me repeat from here, xn is, xn maybe is two subscripts. Let's use a subscript. Xn is j, given x0 is j. Let's call this the probability of event a sub n. Okay, now by Borel-Cantelli lemma 1, okay, we know that if Pan converges summed over all n from 1 to infinity, this means that the events an happen infinitely often. I'm sorry, finitely often, meaning the probability that they happen infinitely often is 0. So this implies that the part B of the theorem, which says that state J is transient. By definition of recurrent, if a state is not transient, it's recurrent. So we have also proved part A of the theorem. So let's give an example of a Markov chain. Let's think of this 3 states or 4 states Markov chain. States 1, 2, 3. There's a transition from 1 back to itself. There's a transition from 2 to 1. There's a transition from 3 to 1 and 1 from 1 to 3. And 3 back to itself, okay, and 2 back to itself, let's say, and 2 to 3. But then there's a state 4 here. From 4 you can go to 2. From 2 you can come back to 4. Now let's see. Let's notice here that if we leave state 2 to go to states 1 or 3, then it is not going to happen again that we return ever to 2 or 4. Again, from state 4, there is a way to go to state 2 and then get lost in states 1 and 3 forever. So states 2 and 4 are transient states. When we leave states 2 or 4, it is not guaranteed that we will come back in the future. Okay, so the probability that we will come back again and again is not 1. So states 2 and 4 are transient, but states 1 and 3 are recurrent. Because when I'm in state 1, no matter where I go, in this case only 3 is a possibility. I can stay at 1 or go to 3, but when I go to 3, eventually I will come back. This is assuming, of course, that we have non-zero probabilities represented by these arrows. Okay, non-zero transition probabilities. Now, as a corollary of this theorem, if a state J is transient, then Pij of n, meaning the probability of going from I to j in n steps, must go to 0 as n goes to infinity for all starting states I. What does this mean? It means that no matter where we start, the probability of ending up in j after a very long amount of time goes to 0 as time increases. This also says that I will eventually not be in the transient states. Let's define n of I as the number of times state I is revisited. Starting from state I, the number of times the state I is revisited. Another corollary of our theorem is that the probability that n of I is infinite is 1 if I is recurrent and 0 otherwise. Okay. I will make another definition, a final definition for this lecture that we will use in the future. Let's define T sub j as the minimum of n such that xn is j. This is the time of the first visit to j, given that I started in state j. Okay. Given x0 is j. Okay. Now, of course, if this visit never occurs, we can set Tj as infinity. Now, we will define Ti bar as the expectation of Ti. But to be explicit, I will put the conditioning here just to make sure that the conditioning that we are starting in state I is included. I am conditioning on being in state I initially, and Ti bar is the expected return time to state I. Okay, this is called the mean recurrence time. And the mean recurrence time may not be defined. It's actually not defined if state I is transient, and may or may not be finite when a state is recurrent. In the case of a Markov chain with a countably infinite number of states, the mean recurrence time being infinite is possible, and we will call that null recurrence. We will say more about this in the next lecture.